All right, good morning, guys. Yeah, this week we do have quite a bit of assignments due. So first is the quizzes. We do have 4 quizzes last week. So yeah, from 19 to 22. Make sure that you don't overlook them. All right. Now those who have already provided the solutions in class, yeah, no need to work on them on the Facebook. Oh, hi. You guys are live. Okay, good. And PA number A is due. And by the way, PA number A is about the most intensive assignment, the PA assignment, okay, this semester. So if you're through with PA 8, you should be safe, okay, on the PA part of the credit. And today, all right, very good. Hi, good morning, Ji Ting, and morning, David. I think you're Yongyuan, right? In Rocket, aka Leo, RNG Silvercraft, I think Yizhou. So I think gradually I'm actually recognizing who you are by your IDs. Good, and the topics for today. So this is actually going to be a brand new chapter. So the things we'll be talking about are completely different. Okay, I don't know about you. This is about my favorite chapter in the whole textbook because this is talking about the core of the internet, and this is mainly how internet is connecting everyone, okay, worldwide. Hopefully, in the future, more that it's neutral and no discrimination. Okay, and the major topics. First is going to be an introduction of the chapter. Okay, you're seeing a little bit why I call it the data plane. And then the second part. So the first part is going to be pretty long. It's going to be 21 minutes because this is completely different from chapter 3 and 2 where we talk about end-to-end processes, how the end-to-end processes are connected to each other. Now this is actually way at the lower level, okay, the network level involving all the routers. Okay, I want to make sure things are clear, so I take it a bit slower, although I still talk quite fast. And then, okay, the second part, that part is going to be only like 12 minutes, okay, and I'm going to introduce you how the router works, okay, and we'll start by introducing this mechanism called the prefix-based forwarding, right? And shortly after we finish talking about prefix-based forwarding, there'll be two quizzes, okay, so that is very important, okay. Internet is forwarding packets based on destination IP address, and particularly the prefix of destination IP address. So we'll have 2 quizzes exercising, okay, the notion of doing prefix forwarding. And let's go ahead and start. Oh, hi Kevin and Peian. Welcome to chapter 4, the network layer, and particularly the data plane. So in this chapter, the goals are understanding the principles behind these network layer protocols. And we'll focus on data plane and talk about the other one, the control plane, in chapter 5. So in the overview section, we're going to talk about the service models possible for these network layer services. And we'll talk about the main functionalities that people implement in the network layer. Forwarding and routing. We'll talk more about these. And we'll be spending some time here talking about the architecture of a router and how packets travel through a router. And the rest of the chapter will be spending a lot more time here talking about forwarding of packets generally, as well as how it's implemented, how it's working on the internet. 4.1, the overview of network layer. Well, what the network layer is doing is simply this: transport segments from the sending host to the receiving host. So let's use the micro internet here as an example. And let's assume this guy here is the sending host and this guy here is the receiving host. So the goal of the network layer service is so that we could send segments or packets through the internet to the receiving host. Now, what's a bit special though, okay, in the network layer? It's not only the 2 end hosts have the network layer protocol implemented and operating on the machine. Each and every router inside the network here would also have the network layer protocols running. Now to be exact, okay, on the sending side, on the sending host here, the transport layer segment is going to be encapsulated into the datagrams. So a packet at the transport layer is called the segment. But when a packet now goes into the network layer, it's called a datagram. And sometimes also called the IP datagram. Okay, so transport layer, TCP layer. Network layer, IP layer. Transport layer, we have the TCP segments. Network layer, we have the IP datagrams. Okay, so at the sending side, we encapsulate these transport layer segments into the IP datagrams. Now these grams, okay, datagrams will go on to the network and travel from router to router. And each of the router will examine something special, okay, in the packet header, in the IP datagram header, okay, and decide where to pass it further on. So that magic we'll talk about more in the sections to come. Finally, when the packet arrives at the receiving side, okay, so this is the receiving host, the network layer is going to look at the datagram, remove the packet header, and pass the segment, okay, up to the transport layer. So that is the lifetime of a packet traveling the network through the network layer. So in anime, so a packet coming from above, pending the header, so packet gets a bit bigger, and you see routers busy forwarding the packet and eventually reaching the receiving host. And at the network layer header or the IP datagram header removed and the segment restored and pushed up, okay, to the higher layer. Alright, so that is the general picture of what the network layer protocol is doing. Now, the network layer protocol is doing two major functionalities. As you observed earlier, yes, forwarding. The routers are all what? Busy moving packets around from one router to another router. Hopefully it gets to the next router that is appropriate so we don't take too much time to pass the packets until it reaches the receiving host. The other is this, okay, this is also the magic that I was talking about. So this is the computation, the intelligence in the network layer that determines, okay, a route between a pair of sending host and the receiving host. Or a lot of times we just call them the source and the destinations. So to determine an end-to-end path to travel over the internet from the source to the destination. And that intelligence is also called the routing algorithms. An analogy is this. Let's assume the class is taking a trip to Canteen. Yeah, I know the weather is getting warm. It would be really nice if we're in Canteen. Okay. Well, the thing you need to do first is this, routing. You pre-compute or you Google, okay, and come up with a plan, okay, for the day of travel. Whether we take a bus to the Taipei station or we take a metro to the Taipei station. And from the Taipei station, do we take the high-speed rail? And from the high-speed rail station at Kaohsiung, do we take another bus or do we all rent a car or rent a number of these bikes so that we ride along all the way to Canteen? Okay, so the computation process, the intelligence that we need to do ahead of the travel is called the routing. Now, on the day of travel, we'll bring this Google map printout saying, hey, you start from home, you walk to a particular station, and you hop on a particular metro line. And once you get to the Taipei station, you just hop onto, high-speed rail number 112. And then after arriving at Kaohsiung, you go to a particular bus stop, and then you hop on the next vehicle taking you to Canteen. So that is this forwarding. Okay, so at every interchange point, you look up a piece of paper and find out what is the next step to do. So this way, it ensures that the forwarding part, the traveling part is going to be fast and smooth. So the separation or the differentiation between the routing function and the forwarding function. And that should make it a bit clear for you to see the separation between data plane and the control plane. So by data plane, we actually meant to talk about the forwarding function. Okay. And the control plane, on the other hand, is the routing function, the part that is trying to identify a path between the source and the destination. Now let's talk a bit more about the data plane. Okay, so what's being done there is very local. Each router is determining for each incoming datagram who should be the next router to forward it further. Okay. And that is the forwarding function. So it's illustrated here. For a datagram coming in, this router here is looking up a table and find out, oh, this should be the outgoing port, and therefore reaching the next router. Now, the control plane, on the other hand, is the part implementing the routing functionality, implementing the intelligence. It is to determine, how would the packets be able to travel end to end from the source to the destination. So these routing algorithms will be implemented in the control plane. Now there are two different approaches implementing the control plane. One is the traditional approach. The other is called the SDN approach. The traditional one is the distributed approach. And the modern one, the SDN one, is actually more centralized. To your surprise, isn't it? We are actually moving from distributed solution to centralized solution. Now in the traditional one, each router will be implementing the routing algorithm, and the routers will also exchange information among themselves. As a result, and collaboratively, they calculate an end-to-end path. Now in this centralized approach, in the SDN, we actually ask a couple very powerful machines, a couple very powerful SDN servers that are actually sitting far away from the routers to do the computation. And then after the computation is done, they're gonna install the routes back into the routers. So the tables are actually computed on the routers locally in the traditional way. But more recently, the modern way is to have some powerful machines computing all the routes and then install them back to the local routers. And local routers no longer do the complex route computation. So let's talk a bit more about the data plane. So this is the forwarding part. So this is the part implementing the per router action. And it's very simple, very fast. All that is done is the packet coming in. The router look at the specific packet header field and match to an entry in the forwarding table. So this is called the fast output interface lookup. Once we get a match, we get also the outgoing interface. Let me illustrate. So these are the routers. And inside the router, you see this is the entire operating system stack. There's this thing called the forwarding table, and each router will have one of these. When there's a packet coming in like this, it's going to look into a packet header field and matching the pattern here to the entries in the table. Now, we see that this guy is the matching entry. Therefore, immediately we see the packet should go out on interface 2. So output interface 2. So this is the direction to forward the packet further, and therefore next is going to arrive here in this router. So this is exactly the detailed step of packet forwarding in the data plane. And the control plane is here, higher up in the operating system stack. To be more exact, and let's talk about the traditional approach first, where the computation is distributed. So the routing algorithm is going to be running on each of these routers, and up here. The routing algorithm here, 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 and here. So each and every router is going to have the routing algorithms running, and they're going to interact with each other. So there are these exchanges of messages between these routing algorithms distributed on the routers. And this is the control plane. As a result of the computation and exchange, they find out what should be the forwarding table for different incoming packet, for different packets going to different destinations. and install the local forwarding table into the data plane. So this is the separation of the control and the data plane. Now, in the modern days, we take the centralized approach, the SDN approach. Now, it looks a little bit different, the separation of the data and control plane. So routers protocol stack, okay, stop right here. Because the computation is all where? Up here. Okay, a couple machines, powerful machines, okay, doing the computation. But it cannot be computing without information provided by the routers here. So these routers, okay, will have a tiny little process running here. They're called the control agent. The control agent here is gonna provide input to the remote controller. This is the big process implementing the routing algorithm. So after collecting information about, hey, who they are and the connectivity of these routers to other neighboring routers, now this controller here can then do the powerful computation. Once the result is obtained, okay, those tables are communicated back, sent back to the control agent, and therefore installed into the data plane of the routers. Before we talk about the service models implemented at the network layer, let me remind you this. If you recall, when we were talking about RDT, we say sending process, receiving process. If the underlying channel is reliable, all they need to do is just to pass data out, and the data is just going to arrive. But unfortunately, the channel is not exactly reliable. Okay? And depending on how unreliable the channel is, the complexity, okay, of the reliable data transfer service is going to be different. More unreliable, more complex. Less unreliable, less complex. Okay. So the service model we'll be talking about next is to talk about how we implement. Okay, what kind of channel we're providing here? Are we going to provide a more reliable channel or less reliable channel? So more reliable channel is one service model. Less reliable channel is one service model as well. And we could actually have a spectrum of different service models here. There are two major camps of service models. First is the connectionless service. What it meant there is that the end hosts and the routers in the middle, they do not set up any connection-specific states before data being passed around. So there's no reservation of bandwidth, no reservation of memory space to buffer packets. Okay, so you see that there's not going to be any guarantee at all. Exactly. So this connectionless service is also called the best effort model. Okay, and this is exactly the model implemented in TCP/IP, the internet. The second camp, the connection-oriented service, which is the opposite. So the end systems, as well as the routers in the middle, they would actually exchange message and establish a connection before the data flows. So this is actually implemented in some of the old architectures, old systems. ATM, this is not the bank ATM machine, banking machine that you use withdraw money. So this is actually a specific computer network that have been designed in the 20th century. At some point, okay, ATM is actually competing with the internet. I think towards late 90s, okay, still before the turn of 21st century, ATM gets merged into the internet. So some of these routers in the internet, the lower architecture design is actually from ATM. Now, frame relay X25, these are just too old. Okay, but these are examples of connection-oriented network layer service. Okay. Now, to establish such a connection will involve routers, okay, and the involvement is actually quite deep. It's complicated enough. It's the third important function, okay, in these systems, on top of routing and forwarding. Now, one last bit I want to talk about is this. We've heard about connection-oriented service as well when we were talking about TCP, right? TCP, they're sending SYN, ACK, and then ACK for the SYN, ACK. Hey, that's establishing connection, right? It sounded very much like these yeah, ATM frame relay X25 is doing. Yes. At the transport layer, TCP is actually establishing connection between two processes. At the network layer, in ATM frame relay X25, they are actually also establishing connections between two hosts. All right? But be careful. Internet at the network layer does not implement connection-oriented service. However, at the transport layer, implements connection-oriented service. So, just be clear. Internet, the subject we're talking about and we'll continue to talk about, does implement connection-oriented service at the transport layer, but not at the network layer. Internet, in fact, when it is designed, it does have this complexity at the edge mindset so that we don't do complex things in the network layer involving the routers. Yeah, those are the major camps. But within each camp, you can probably define finer service models so that you provide different levels of service. So, for example, we could actually come up with services for individual datagrams, such as guaranteeing the delivery of a particular packet, guaranteeing the delivery of a particular packet within 40 milliseconds. We could also try to provide services guaranteeing the flow of a number of packets. So we ensure that these packets will arrive in order, or we guarantee a certain bandwidth, or we restrict the time differences in between these packets when they arrive. So again, the service models, they can be finer, or coarser. It's more like a spectrum. Now what I'm listing here are the 5 services models that have been implemented and being used, at least for some time, in ATM's case, and continue to be used today on the internet as well. So the internet service is, the best effort. So essentially it's not guaranteeing anything. No guarantee at all, and it's not giving condition feedback from the network layer. It's in fact being inferred from the transport layer, between the TCP sender and receiver. Now ATM, quite sophisticated, provides actually a spectrum of service models. The CBR stands for constant bit rate service. So it actually guarantees a constant rate. So this is perfect for the constant data streams. It guarantees such that there's no loss, packet arriving in order, and the timing of the packets is also guaranteed. It's going to be constant. And there's not going to be congestion at all, so there's no need of congestion feedback. Variable bit rate service. So this is actually guaranteeing the maximum bandwidth required by a variable bit rate data stream. So there's no loss because we are guaranteeing to the maximum rate, right? So packet arriving in order, there's no delay as well, no congestion. So you see here, these two are highly guaranteeing everything, but one for the constant data stream, this one is for the variable rate data stream. Now these two, however, available bit rate service. So this is only guarantee a minimum rate. Therefore, there could be losses and the timing cannot be guaranteed because there's a lower rate. Packet could arrive faster than they can go out. So they could get buffer, they could get dropped at the buffer. But in ATM, even though there's no guarantee of the bandwidth delay, but there will be explicit congestion signal back to the data source. And UBR, on the other hand, in ATM, so this is the minimum level of service in ATM. It's called the unspecified bitrate service. So there's no guarantee of bandwidth, no loss. Packet will still be arriving in order. That's special about ATM because it's, after all, still a circuit switch network. And there's no timing guarantee. And in this case, no longer a congestion signal going back to the data source. So you see, again, network layer service model, it can be a full spectrum. Just that unfortunately in internet, or fortunately in internet, There's just one model we talk about, the best ever. Okay. So, how do you like the layer? Okay, it's actually quite curious, isn't it? Yeah, there was a question. Wow, okay. Hey, I was asking. Yeah, is speeding up the main purpose of using SDN? It is one of the big purpose, okay? But there's yet a couple other big purposes. One is debugging, the other is management, okay? So by management there, I meant to have some flexibility. So for example, big companies like Google, they have data centers here and there. What they do a lot is to do data synchronization in the background past midnight. So it would be really nice to set up some sort of guarantee so for big data to be passed around between the data centers. So management purpose, having some level of flexibility. Another is debugging. I don't know, this is actually arguable for many network operators, for many big ISPs, particularly the backbone ISPs. Internet is so big now. Okay? It's so complex. It's one of the biggest distributed system existing. Another feature of internet is this: we're using it every day. It's almost like electricity, the importance of it, the significance of it, right? If there's a power outage, I mean, we're gonna all jump, just like when there's an internet outage, right? Using it at home or using it in this semester, right? If there's no internet, there's not much we can do, okay? Cannot get work done, cannot get study done, okay? Cannot get teaching done, all right? So it's actually concerning our everyday life. If there's a hole in the internet or infinite loop in the internet, data is just not going to the places they're supposed to go. It's a huge problem, okay? And the original internet's data plan and control plane, it's completely distributed. It's actually very hard to debug that way, although every router is doing a small part of the computation, okay? If you think about it in terms of computation cost, computation load per router, that is the best way to go. But okay, if managing it, debugging a route, okay, debugging an outage, okay, that is actually a big headache because you don't know exactly. You have to do tracing, okay, one router at a time, and it could take days, okay, just to isolate a routing problem. So that is actually the main motivation of having SDN. Okay, otherwise having these remote machines doing the computation and the computation being centralized, it's obviously not going to be efficient. Okay, many network engineers actually dislike and veto the proposal at the beginning. Okay, it's only until more recent decade. Okay, people start seeing these problems at the operation. Okay, operational side of the internet. Then people giving. Okay, the engineers giving. All right, so that's a very good question. Okay, we'll see later in I think the last section in chapter 4, okay, how the SDN is doing the forwarding part. Well, there's another question. Are traditional methods all replaced by SDN now? Oh, that's also a very good question. How you know what? Not. Okay, because SDN routers are quite expensive. Okay, so these powerful machines, quite expensive. There's also a steep learning curve. There are not many network admins who know how to program these SDNs so that they would install the routing table appropriately to these different routers. Okay, so the basic routers need to be updated, and you need to have these additional remote machines doing the route computation. And the configurations are way more complicated. Okay, so a very experienced SDN network admin in US is very, very high paid. Let me just put it that way. All right. I think Cisco probably also offers some certificates for SDN-based route system admins. So you could look it up if you're interested. Okay. Yeah, that's the second question. And then now let's take a look into the routers. Okay, it's actually quite an expensive hardware as well. But for now, we'll be just looking at the data plane. Okay. Later on in the last section, again, as I said, we'll look at the SDN's data plane later. Now let's take a look into the inside of a router. So this is the traditional router. This is the general architecture. We do have a processor, which is doing the routing algorithm. So the complex route computation is being done here. The processor is quite high-end, very much comparable to the CPU, high-end CPUs we're using these days, except that the processor here might be a bit more optimized for route computation. Second most important entity, the switching fabric. Well, people will argue this is probably the most important entity because this is the part of the router that is doing the actual switching, the actual moving of the packets. Okay? And we know that the packet needs to be moved very, very fast. So these switching fabrics definitely needs to be high speed. Third, the input and output ports. Okay? By output ports, input ports, I actually meant that these network interface cards, okay, that we use to connect to the routers that are, passing data in, passing packets in, as well as connecting to routers, okay, that we pass the packets out. Okay. Now, you see then, yeah, the lower part is where the packets are flowing through. So this is the data plane, meaning this is the part of the router that we are flowing the data. So the functionality there, very important, just to move packets. In order to be very, very fast, yeah, the computation, the switching there is pretty much hardware optimized. And so they can work in this time scale, the nano time scale. On the other hand, the upper plane, that is the control plane. Now we have the routing algorithm implemented as software running there. So in addition to routing, it does also a little bit of the management of the router. Okay? For example, tracking, monitoring, how many packets coming in, how many packets going out, things like that. Okay. Now, this part being implemented in software then operates in a slower time scale, the millisecond time scale. Now, the one most important functionality for the router to do is forwarding. Now, it also does route computation here. Okay. Now, connection between the route computation and the forwarding here is this. After the route is computed, we install the forwarding table into the memory of the incoming network interface here. Okay. Let's zoom in a little bit more into the input network interface so that we see a little bit more the forwarding functionality. Where does it happen? And it's happening right here. Okay, the component that's connecting the input network interface to the switching fabric. Okay. So what's being done there is essentially switching, and it's done in a decentralized way, meaning for each of these input port, each of these input network interface, there's a lookup processor. Okay. So the forwarding of packets coming into each of these input ports is done parallel across all these input ports. So that's what they meant here, decentralized. So each lookup processor here is doing this. It looks into the header fields in the packet. Okay. And it's seeking the output port using a forwarding table that's installed from the route processor, and that is installed already into the input port memory here, okay, right here. So the goal here for the incoming network interface is so that it can complete the input port processing, the lookup forwarding at the line speed. Okay? Meaning, if this is the speed of packets coming in, now this forwarding process needs to be fast enough so that we get the same output speed here. Okay. If this is slow and this is fast, so if this is R prime and R prime is smaller than R, then we will end up having this. Okay. Packet gets queued. Packets need to wait somewhere in a temporary buffer before they can go out. So that's queuing. Datagrams, if they arrive faster than going out into the switch fabric, then there's queuing delay. Now, there are two different kinds of forwarding. In the traditional internet, we do the destination-based forwarding, which is to look at the packet header fields, particularly the destination IP address, and only the destination IP address. Now, in SDN, the modern routing, it's called the generalized forwarding because we can actually look at multiple header field values, not just one. And it can be arbitrary combination of these header fields. Okay. So it's a lot more general. But you can also see that provided the same lookup processor, okay, this is going to be a bit faster and this is going to be a bit slower. So in order to keep up the speed, okay, if the incoming is R and output is R prime here, in order to make sure this R prime is as high as possible, usually in SDN, okay, these SDN routers will need a faster lookup processor here. So this one here, SDN routers, more expensive, while this one here, usually more affordable. So that was the router architecture. Now, there's one thing I want to talk about which is very, very relevant to the rest of the chapter. Okay. Destination-based forwarding. Okay. As you heard, forwarding is based on, for each packet coming in, look at the packet header field and try to match an entry in the forwarding table. Okay. So if the destination address says this, 11001000, matching this guy here, then we take this output port, okay, output link interface. If it matches, for example, this IP address, okay, then we take output port 2. What happened inside this forwarding table is, if you think about it, right, there are so many possible destinations on the internet. And for each destination, there needs to be an entry, isn't it? So this is this particular destination's output interface being 0. So in fact, okay, in a forwarding table, you should be seeing for each possible IP address, what is the output link interface? For each of these IP addresses, what is the output link interface? But the thing is this, okay, how many possible destinations there can be? Well, the IP address is this big. Okay, the IP address, 8 bits, 8 bits, 8 bits, 8 bits together, 32 bits. So you could have actually 1 gig entries. Okay. And each entry might require, you see, 4 bits, 4 8 bits, that means at least 4 bytes, and maybe another byte here for the link interface. So each entry here at least needs to be 5 bytes. So 5 gig, 5 bytes, and that will be 5 gigabyte at least, just to keep the forwarding table. Okay, so the input port network card there, okay, it's gonna require not just a high-speed lookup processor, but also a lot of memory space. In addition to the buffer space might be required, right, in case queuing occur. So that particular interface there is already very costly. And if you need to have many input ports, many output ports, think about the cost of a very high-end router, very expensive. And that's not going to scale very well if we actually, expands the IP address space. So this is 32 bits IP address. This is IP version 4. Later on, you will see. Okay, there's another version of the IP layer protocol. That's called the IP version 6. And the address space there is actually expanded to 28. So this approach, each IP, each entry, is not going to scale very well. So what's really being done on the internet is this. We do matching, all right, but not match the entire IP address. We only match the prefix, okay, of the IP address. So we're doing table lookup is to do matching, but we are only matching to the longest prefix. Okay. So this is what we do when we're looking up in the forwarding table entry. So given the destination address, okay, so we'll take this address and match the entries here. Okay, this time we don't have one entry per IP address. It's actually an aggregated or the prefix. So what you're seeing here is we only specify the first part of the IP address and leave the rest general. Okay, so that is also saying that as long as the destination address, the first few bytes match this pattern, okay, the rest of the IP address can be general, free. Okay, now as long as you have a destination IP address looking like this, then we take this packet to this output port. And the second entry is saying that, okay, if the IP address matches this pattern, the rest can be flexible. No matter what, we go to output port 1. Now, there could be multiple entries. For example, this guy here and this guy here, you see here. Oh, up to this point, they are the same. So you could have an IP address matching both entries, isn't it? So in this case, we'll take the longest prefix. Okay, we'll take the entry that the destination IP address matches the longest. Okay, now, in case the rest of the 3-bit of this IP address is 000, then we forward that packet to output 1. If it's something like 101, then it does not quite match this entry. However, matching this entry, then we send it to output 2. All right. So let's exercise a little bit. Now, if we get a packet, the destination address is this. What should be the output interface? Let's see. The first 8 bits match. Great. In fact, all these 3 entries, the first 16 bits, actually 19, 20, yeah, the first 20 bits are all the same. So these two destination address, I think the first 20 bits are also the same. So what differs is beginning from the 21st bits. So which entry in the forwarding table does the first destination address match? Well, this is 0. So only this entry match, right? Because this is 1, this is 1. So these two not matching. Therefore, this packet goes to interface 0. Now, the second destination here. Oh, 21st bit is 1. So it should be either one of these. Now, 0, 0, 0. Well, it actually matches more the second entry. Therefore, the outgoing interface for the second destination address being 1. And that takes us to a double quiz time. All right. So I'm not sure if we have time for double quizzes, but at least we could go over one. And before I go over the quiz, I think there's a couple questions here, both from Kevin. Okay, does forwarding table in the router change? You know what? The table does change, but it's usually when the routes get changed. Therefore, the table gets reinstalled. Okay, and Kevin is asking further. Okay, does the forwarding table get changed due to a network situation, such as congestion, okay, in some routers? You know what? That might happen, that might not happen either. Okay, it depends on the routing algorithm. So some of these routing algorithms actually take into consideration of the network load. Okay. In chapter 5, you will see. So there'll be some algorithms that we go over. So yeah, it's graph algorithm. Could be a little bit complex for some of you. So eventually, right, to figure out a route from the source to destination, okay, if you do have a route that costs you $20 versus another route that costs you $10, you pick the one with the $10, okay, cost. Similarly, right, you could actually use a metric such as congestion level. Okay, if this route here is congestion level 20 versus another route congestion 10, then you might take the route being congestion 10. Now, with that kind of routing algorithm running, with the congestion happening in the network, the route can actually change, therefore triggering the forwarding table being changed. Okay. So there's certain relationship, there's a certain connection between the routing algorithm and the forwarding table. The forwarding table does not get changed because the forwarding part, the data plane of the router, is detecting something itself. It's more that the control plane part is detecting it, okay, and then enforce the forwarding table to be outdated. All right. I hope that is slightly clear. Okay. Clear. Now, quiz 23. We don't want to get this quiz over with today. So, hey, let's exercise longest prefix match. Okay. The forwarding table is exactly the same as the slide we just went over. There are 3 entries, right? The first one is actually ending with 00010, and then the last bits are all sort of wild cards. Okay, so that particular matching entry is going to take you to interface 0, and so on and so forth. Now, the last one is otherwise, meaning, oh, wow, okay, team 2, okay. So I have not yet explained the question. So otherwise is for all other IP destination address not matching the previous 3 entries. Then we take interface 3. Right? So DA, the number 1 is asking which interface for this destination address. So you see the 1, 2, 3, the third octet here, okay, is the part that's mainly being different. So it matches 0001. Oh, the 5th bit in the third octet does not quite match the first entry, isn't it? Does it match the second entry? Well, it matches to the 5th bit, but the 8th bit, it's no longer matching either. So the first 2 entries are no match for DA1. But the third entry, yeah, cool. It matches all the way to the end of the prefix. Yeah, I think many of you guys were saying, yeah, quiz 23, Q1, link 2. Yeah, so team 2, you've got it right. And team 13, yes, you've got it right as well. Okay, so Q1's DA, it matches only the third entry, which is going to link interface 2. Team 5, very good. So if you may allow me going here. Yeah, so the Q1's DA, it matches all the way to the 5th bit, right? To entry 11. Yeah, the first 5 bits of entry number 3. The first 5 bits of entry 2, although match the DA, but hey, longest prefix match is actually matching to the end, all the way to the end, right? So by looking through all the bits here, okay, all the way up to the 8th bit, you see that Q1's DA does not match this. Okay, so this is obviously no match, and therefore we match only this entry. Now for Q2, okay, does it match the first entry? The 5th bit doesn't match, so nope. For the second entry, we match to the 6th bit, in fact, right? But beginning from the 7th bit, not matching. Okay. And then again, yeah, entry 3 matches, therefore, for Q2, we also take the link interface 2 to go out. Similarly for Q3, let's go over this. Does it match the first entry? Well, 0, 0, 0, but hey, the 4th bit is 0, so it's not matching entry 1. Not matching entry 2. Not matching entry 3. And the only one left is just the otherwise. So for Q3, we'll take interface 3. Alright, and I hope that is clear for you guys. Okay, very good. So David is fixing the solution for Q3. Alright, good. You guys all got it. And that is actually all the time we have for today. Tomorrow, okay, beginning of the lecture, sorry. Yeah, you have to wake up in order to work on Q24. It's actually to generate the table yourself for longest prefix matching. Okay, I'm leaking Q24 a little bit ahead. In fact, you can actually go to the Facebook board. You should see that these quizzes, sometimes they're already in there before the lecture. Okay. All right, good. So that's all for today, and hopefully I see you tomorrow. Hopefully waking up by 10:20. Yeah, I think that's all. I'm gonna leave the session on for just a few more minutes and see if you guys wanna answer quiz number 23. Let me go back to quiz 23, right here. Looks like Jiazi is very curious, right? Yeah, it is determined by the routing algorithm. So when we're in chapter 5, I will actually demonstrate after the route computation how we generate the forwarding table from the computed routes. Because you guys are wondering why, how come? Yeah, matching that prefix, then the link interface should be 0. Link interface should be 2. Yeah, it's actually not like randomly generated. There's some intelligence behind, and it's a result of route computation. So, Jiazi, you are guessing it right. It is the routing algorithm there determining how the forwarding table is going to look like. And don't worry, I think later part next week we're going to begin talking about routing, so it's not actually too far away. Yeah, I'm not quite sure that we'll be able to finish chapter 4 this week. No, I am pretty sure already. So there will be some part of the last part of chapter 4 being in next week's lecture. But we will not need the entire next week for the forwarding part. So chances very high that beginning next Thursday, we'll begin talking about routing, route computation in traditional internet. But the SDN part might be in the next week. And by the way, this semester, we just have very short semester. There's no way we talk about the link layer, unfortunately, if we want to deliver the content through clearly. So the network layer is actually the most interesting part of the internet. I understand for many of you guys, the application layer protocols are fun because you're using it. A lot of you are using many of them every day, so you feel like they're familiar. But really, in order for the internet to work all these application level magics, not having the network, not having the TCP, not possible. Okay, so there are these sort of more fundamental layers that you guys know less about. And that is the whole point of running this course here, okay? To fill you in with the lower layer backgrounds. All right, so, okay, yes, we'll learn more about it. Okay. So Sorry, I keep asking you guys to be patient. I know when you run into interesting subjects, you cannot quite wait. That's the same thing that Polly also feels all the time. And by the way, link layer is also extremely interesting. It's just that unfortunately this semester we don't get to talk too much. Okay. Okay, guys, go to lunch. I'll just end the stream right here, and I'll see you tomorrow.